Tell you the meaning of music, yo. I must appeal to you people with your faculties, cause everybody else is gonna laugh at me. People try to get over and take a crack at me. The universe is one, I see what rap can be. Glorious, put in the Smithsonian on podiums for holy hymns. But you see who's controlling them. Fuck myself off.
In this video we'll consider the electric potential due to point charges only. They're a little bit more complicated than the case with parallel plates where we have constant electric field. So let's see how it works in this case. So here we have a positive charge Q. It radiates an electric field in all directions. And let's put 2 points. Here's point A, and here we have point B. So this is the distance from the charge RA, and here we have distance RB. Now let's calculate what is the work needed to be done if we have a charge Q placed somewhere in this field. We'll start from point A and move it over to point B. So the change in electric potential will be VB minus VA. VB must be larger because the closer the positive charge, and the test charge itself is assumed to be positive. So this is the line integral from point A to point B along the electric field. And we can express the electric field for the point charge to be K times Q and sorry about that, R squared, point dr, or in this case, instead of L, we have, of course, dr. If we carry out this integration, we'll get Q times Q and 1 over RB minus 1 over RA. In the case of point charges, or whenever we're dealing with electric potential, we usually define where is the zero potential. And in the case of point charges, it's always in infinity. So in this case, we define our point A to be in infinity, and over there the potential is agreed to be zero. So if RA goes to infinity, this one goes to zero, and we decided the VA is zero. So in fact, we get for electric potential at some point B, Q times Q over RB, where RB is the difference or distance from the source, or in general case we can say the potential to the point charge is KQ over R, and we can also write this in the form Q times 4 pi epsilon 0 R. Or let me rephrase again what I said. So this is the electrical potential that the charge Q experiences in the vicinity of another charge q, or in other words, the potential that it experiences in the field generated by charge q. Here we have plots of this function for two different cases. The first one is when generating charge is positive, like over here. So as we see from this formula, or this one, as the R increases, as we go further away from the charge, the potential energy drops and approaches zero in infinity, like we agreed. On the other hand, if we have negative charge that is generating the field, then we have the Q is negative and it flips the function or the graph upside down. So in this case, this is what we get. If you think about it in terms of gravity, here we have electric charge, a positive charge. It needs to go uphill, and that requires some work in order to make it go closer to the other charge. But on the other hand, if we place a positive test charge here, it will happily fall down the hill towards the negative charge. And the opposite would be true if we had a negative test charge. The negative test charge would happily climb up the hill, but we would require a lot of work to make it fall down. So whenever you're dealing with charges and these uphill and downhill analogy, you have to be careful with your signs. They will reverse for the negative test charges, which means for negative test charge, uphill is in fact downhill, and downhill is in fact uphill. What about if we have two or more charges that are generating the field, and we want to calculate the potential or electric potential in that field? So let's say we have a positive charge here and a negative charge there. So let's call this Q2 and this would be Q1. And then we have some test charge over here, that's Q, and this distance is R2 and this distance is R1. Also in this case, like with electric field or the Coulomb's force, we can use the principle of superposition. So we can just add up the effects of these two charges. So the total potential of the charge Q in this field generated by these two charges would be just potential relative to Q2 and plus the potential from Q1 V1, which will be K times Q2 divided by R2 plus K plus Q1 divided by R1. The nice thing about the electric potential is that this quantity is a scalar. It has no direction. So unlike, for example, in case of electric field, we had to consider what is the direction of the field at this very point. But the concept of potential doesn't require that. So that's one of the reasons the electric potential was introduced in the first place, to make calculations more simple, where the knowledge of the actual field is not needed. Exercise C asks us to calculate the potential at a distance of 3 centimeters from a negative point charge. The potential is simply K times Q times the distance from the charge. So K is 10 times 9 times 10 to the 9 Newton meter squared times Coulomb squared, and our charge is negative 2 times 10 to the 9 minus 9 coulombs, and the distance is 3 centimeters, 0.03 meters. Plug in the numbers, we get minus 600 volts. Remember, whenever the charge is negative, the electric potential as a function of R looks something like this. So it has to be negative. In exercise D, we have 3 pairs of charges, and we are supposed to evaluate their potential energies. So what is meant by the potential energy of this system is, for example, what is the potential energy of this negative charge in the field produced by the positive charge, or the other way around, what is the potential energy of the positive charge in the field of the negative charge. The result is exactly the same, so we can just consider whichever case. So we know that the potential energy of any charge is the electric potential times the charge Q. So let's call this one Q, and this one would be Q here. We can write the potential of this charge Q in the field of Q simply by K times Q and the distance between the two, and then we have our test charge. So from here we can see, because Q is positive and the Q is negative, so these 2 pairs will have negative potential energy. So, but in this case, the both charges Q and Q are positive. So the third set, I, will have positive potential energy. Then, which set has the most negative potential energy? By most negative, we mean how low we are on this curve. So pretty much the magnitude of this expression. So the magnitude is largest when the R is smallest. So the first pair would have the most negative energy. And which set requires the most work to separate charges to infinity? The answer is also in this case the first one, because the first pair, its potential energy is deepest down. So if, let's mark it here, so the first pair would be somewhere here, and the second pair would be somewhere here, and the third pair would be, it's on the other curve. But it would be, its magnitude would be somewhere between the two, because it's not quite as far apart as these two, but it's closer than these two. Anyway, so we see that the first pair is deepest in the so-called potential well, so it has the highest hill to climb to get to the 0 level of potential, which means infinity, or taking them infinitely far apart. In this case, it's not an uphill, but the idea is the same. What is the distance of the potential from the 0 level? and it's definitely largest for the first pair. Qualitatively, this makes sense. So if you look at this pair, they're closest to each other, so the attraction between the two is the largest, so it's hardest to pull them away in the first place.
Everybody suspect, I must check your ID. Cause you looking shiesty, you might be intelligent. Someone that deals against opposite of positive. When I drop the laws against a nature, be faithful. Why should I hate you? We ain't that different. We may act different in some ways, but we still group together like a fucking survey. Suffering and fuck 'em off the motto. I'm trapped in a bottle, my music's getting hollow. And that's what happens when humanity